So now we're going to turn our attention to molecules and compounds. Going from atoms, elements, to forming molecules and compounds through bonds. So we know this to be the case. We know that there are elements, hydrogen or oxygen and hydrogen, and they form compounds, what we know is water. We know that there's 2 hydrogens for 1 oxygen, so we can write the formula H2O. Okay, what we're going to do now is try to focus on how they form, and why is it H2O and not H2O4 or HO. And a lot of that information we're going to garner from our information we just discussed about the electron and, of course, the octet rule. So it turns out that there's 3 types of chemical bonds that we can discuss, and those are listed here: covalent, ionic, and metallic bonds. In general chemistry, we primarily focus on covalent and ionic bonds, but we'll continue to look back at metallic bonds from time to time. Okay, most of their properties can be derived from the names. Okay, we see co is sharing, valent, sharing valence electrons. So covalent bonds are when 2 atoms share 2 or more, as we'll see, valence electrons. Okay. The next one is ionic bonds, and this is the electrostatic attraction between 2 oppositely charged ions. So the attraction between a cation and an anion. We know that opposites attract. When they do so, that's what we refer to as an ionic bond. This doesn't necessarily need to occur, but it often occurs from the transfer of electrons from the cation to the anion. Okay, and the metallic bonds are each a composite or an aggregate of metal atoms, many metal atoms, sharing lots of electrons in a sea of electrons, or what and most people more correctly refer to as conduction band. Okay, so we've got electrons that are mobile and they're floating around in this conduction band, and there's lots of the metal atoms that are attracted to them, and their shared attraction keeps them together. So it's sort of like a covalent bond multiplied through many different atoms. Okay, we'll often hear this as the sea of electrons model. Okay, so let's take a little closer look at some of the bonds. Here we have the covalent bond, or a representation of the covalent bond. And very important to note that if we have 2 nuclei that are sharing valence electrons, it is not the 2 nuclei that are attracted to each other. In fact, because of the positive charge in these nuclei, these 2 atoms would be repelled from each other. So let's say this is a hydrogen atom, H2, or excuse me, a hydrogen molecule. The 2 nuclei of hydrogens atoms would repel each other, but they have a shared electrostatic attraction for the electrons that they both share. So their attraction, this atom's attracted to the electrons, this atom's attracted to the electrons, and that's what keeps them together. Now the arrangement, of course, will try to achieve the lowest potential energy. If you're sharing electrons way up here, we have repulsion here. This configuration would be very amenable to the atom on the right, but this further bond would decrease the attraction, increase the potential energy, and of course there will be potential, the repulsion in between these 2. Okay, so the lowest potential energy will dictate the formation or the shape of these covalent bonds. Okay, so as we said, ionic bonds are the electrostatic attractions between a cation and an anion. Here we have sodium and chloride, which we know is sodium chloride, NaCl. Okay, This can occur from the transfer of electrons. A neutral sodium atom with 11 electrons, 1 valence electrons, would love to give an electron to chlorine to get octet rule. And chlorine, of course, with 7 valence electrons, would love to gain an electron to get to the octet rule. If they do so, they will form cation and anion, and that electrostatic attraction will form the ionic bond. Okay, very different from a covalent bond is that ionic compounds exist in a large array of anions and cations that are shared, have an electrostatic attraction for many other ions.